Okay, so I'm just going to take a few minutes and go over just a tiny bit of what we were going to do today in class. This stuff should be reviewed for you, I think. I'm having a little trouble here with my camera. Looks kind of fuzzy to me. Try that again. Okay. So I just want to go over some of the basics of chemical bonding. We're not going to get into any of the really difficult stuff here, but let's just think about it a little bit. If I have two atoms, I could really say or more, or two ions or more held together then I can say I have a chemical bond. So that's like a super simplified definition of a chemical bond. And you should remember from Chem 1, there are three basic types of chemical bonds. And you should probably at least be able to name two of the three, but we're going to go through them here really quickly. The first one I'm going to talk about in general, ionic bonds. We've been working with those indirectly kind of all year. I would say that these are due to electrostatic charge between, if you think about this, you'll know, between oppositely charged particles. So if I have an ionic bond, we already know this, we have oppositely charged particles that are attracted to each other. These oppositely charged particles we call ions. And we know that if we have an ionic bond, we have a cation, which is always written first, plus an anion. So we've got a positive charge and a negative charge. And we also know that this always ends up to be a metal plus a non-metal. I know some of you are still having a little trouble remembering that. But we have a metal plus a non-metal. When I see that, I know I have an ionic bond, and it should make me go to my periodic table or go in my brain and think, okay, what are the charges of these things? And I'm going to kind of try to stick with a simple example as I go through this. So it could be like Na plus Cl minus. That's an example of two ions coming together to be chemically bonded, and then over here, of course, I would just have my simple old salt, NaCl. So that's very, very basic description of ionic bonds. Of course, we're going to get a lot more in depth, but I just want to hit the three to begin with and show you one other thing this morning. The second type that I'm going to talk about, I think I'll take covalent next. Covalent bonds would be type number 2. So when I'm talking about covalent bonds, I'm talking about molecules forming. And we should know that these things form due to sharing electrons. There's no complete transfer of those electrons. We should also know that these things show up as a nonmetal a non-metal. And they form what we call molecular compounds. The simplest molecular compound I can come up with for an example would be H2O. And we'll spend a lot more time talking about that, about water later on this year, but we understand, or we should know, that water is a molecular compound. When I see a non-metal plus a non-metal, I know that I have no charge on either one of those. Instead, I have sharing. And that's just a good way to think about it. This sharing, it may be equal, or unequal, and we'll talk more about that later. Okay, so then, let's think for just a minute about the third type. This is the one, in Chem 1 we spend way less time on it, so it's the one you guys probably remember the least about. But the third type is metallic bonding. Obviously this is a metal plus a metal, and when I have this type of a compound formed, let's say a metallic compound, when that happens, the electrons are fairly free to move around. We call that electron flow. And because they're able to flow from one element to the next in this bond, this type of bonding is called sometimes the metallic sea, as in ocean, not the letter C, because those electrons are free to flow about from one atom in the compound to the other. This is what gives metals their traits, the characteristics that they have. You know, like, we'll talk a little bit more about them later, but like their conducting, their malleability, their ductility, and a lot of those. So when we think about that, we have to understand that when we're looking at a metallic bond, electrons are free to flow, but they still hold atoms together. So they're still bonded, but those electrons are moving back and forth between the atoms. And that's the reason, I guess we should probably write that down, reason metals behave as they do. So then I could say to you, give you a question maybe like this. What determines the type of bond? Well, when we really think about that, it's a pretty simple answer. What determines the type of bond, really, is the electronic structure. And when I say that, I mean like, how many electrons does it have? Where are the electrons? Does it want to keep them? Is it more beneficial to share them? Is it more beneficial to give them up? So we have to think about all those things. It's the electronic structure of the atom. And that's what allows us, or what determines what type of bond is going to form, how that atom is arranged, what type of atom it is. So then, two other things that I wanted to go over here really quickly that should be fairly simple. Lewis symbols used to represent atoms, and the octet rule. One of the questions you're going to have to do today is over the octet rule, and I think we should know what the octet rule is. We'll talk about it in just a little bit. These electrons involved in bonding we know this, they're called the valence electrons. And for most atoms, these are the electrons in the outer shell. The way that we track outer shell electrons is by using Lewis symbols, sometimes called Lewis dot structures. They're both the same thing. If I have a Lewis symbol, or I'm making a Lewis symbol, then I would say we use the elements chemical symbol, and I would go on a little bit further and say that we use a dot to represent each outer shell or valence electron. So let's look at something really simple so we can do it quickly. Let's look at carbon. If I have carbon, I know I have 1s. I'm going to fill it. I have 2s. It can be filled, which leaves me with 2p, and I only have 2 electrons left. So there I've used all of my electrons. Then I could write that as 1s2, 2s2, 2p2, or I could write He 2s2, 2p2. So when I look at that, I can say, okay, so this tells me there are 4 electrons, or valence electrons, however you want to say that. When I want to write my Lewis symbol, I'm going to take the chemical symbol of the element, and I place it in the center. I know that I have 4 electrons to place around my carbon, and I do this in a very specific order. So I go top, bottom, right, left. So I probably should write that down. Top, bottom, right, left. And I would repeat that if I had more than 4 electrons to do or to work with. So I just follow that pattern no matter what I'm doing. If we look at the periodic table, we already know that we have a pattern. So we know we have a valence shell electron pattern. We've talked about it many times. And that's just simply the number of electrons in the outer shell. I know I have 1 A, 2A, 3A, which is actually for us sometimes group 13, 4A, 5A, 6A, 7A, 8A. So this runs 13, 14, 15, 16, 17, 18, depending upon how the periodic table is set up. We know that in the middle we have those groups 3 through 12, but we don't have a real distinct pattern in always. If I look at this up at the top, this 1 through 8A, we should remember this tells number of valence electrons. And look at this and know, oh, everybody in group 1A has 1 valence electron, 2A, 2 valence electrons, 3, 3, and so on and so forth until I get down here to group 8 or group 18, where I have my noble gases, and I know everybody there has 8 electrons in the outer shell, of course, except for, with the exception of helium, it only has 2 because it only wants to fill its 1s level in its electron configuration. So our periodic table gives us a nice key as to how many electrons, valence electrons, are in the outer shells of the elements, and that makes it a little bit quicker when we're doing Lewis dot structures or when we have to show them quickly or just think about it quickly to use them. Then the last thing I want to talk about really quick is the octet rule. And that is not a good word. All right. Octet rule. Basically, like a really good definition of the octet rule is that atoms gain, lose, or share electrons, let's say, to achieve noble gas configuration. A shorter way to say it. So basically that's their goal. If I have an octet in my valence shells, then I have a full S sublevel, and I have a full P sublevel. We have 2 elements that don't want an octet for sure. Now, not all of our transition metals always have octets. We'll talk about that later. But we have 2 elements that never want to have an octet. That is hydrogen and helium, because both of these guys only want 1s2 full, because they only have 1 energy level. So they only have those 2 sublevels in which to place their electrons. The other way I can think about an octet is 4 pairs of valence electrons. Of course, I just said there are some exceptions here. We also have some exceptions when we look at, I'm just going to make a brief note of this and we'll talk about it more later. Some exceptions within the transition metals. Okay, I think that is a good place to stop, and it will allow you to complete some of what I'm going to put on here. We'll pick up hopefully on Monday where we left off there, and I hope you guys have a great weekend. See you later.